Okay, how about a little assistance with the Module 1 assignment? It's 1 point per question. Let's begin by saying in our own words what we think an observation is. How about an observation is a statement, something you say, right? Like, I feel cold. Based on, well, some sense, so I'll say based on a sensation. My own words, I made it up, seems legit to me. I'll let you do the other ones. We'll scroll down. I'm going to do one from a density problem. Let's do number 4. What's the volume of an object that has a mass of 7.9 grams and its density? So they give you grams, they give you density, you have to do volume. But I do know that density equals mass divided by volume. And that's the same as density over 1 equals mass divided by volume. I do that so I can now cross multiply. I'm going to try to figure out what volume is equal to. So on this side I have density times volume is equal to mass times 1, so just mass. Now to isolate volume, I'd love to see what volume is equal to. I'll get rid of density by dividing it by itself on both sides, because density over density is equal to 1. So if I do the same thing on the other side, I'm not really changing it. So volume is mass over density. I do have the mass. Now I'm not going to write 7.9. I'm going to write 7.9 grams. Always include your units. And the density is 1.28 grams per ml. Uh-oh, milliliters is on the bottom. I'd like the fact that grams canceled, so that's gone. I'm trying to get volume, but why is it on the bottom? It's not really, it's on the bottom of the bottom. 1 over milliliters equals milliliters, and that is equal to, I'm going to put it over here, I guess. What did I get? 6.172 mLs. But analyzing this, we have 2 sig figs here and 3 here, and the rule is when you're dividing, we keep the fewest number of sig figs, which is 2. So I'm going to answer this to 2 significant figures. So the answer is 6.7, oops, 6.17, but I only need it to 2 sig figs. I have to round up. 6.2 milliliters. Don't forget your number and your units as well. Fine, let's go to another one. Energy and heat capacity. How about this one right here? We're taking some hydrogen. I'm just going to call it H. I'm going to combine it with some nitrogen, and I'm going to turn it into some ammonia, which I'll just call A for now. I took 4.9 grams of the hydrogen. I combined it with 9.4, and I better end up with, that is 14.3 grams. I better end up with 14.3 grams. That means mass is being conserved. Well, we got 11.4 plus, what did we have? 2.9 grams remaining. 13.9, 14.3. It checks. Notice that that really means that only, I believe, 2 grams of the hydrogen reacted, leaving you with 2.9 grams unreacted. In either case, any way you look at it, let's see. Determine if the results follow the law of conservation of mass. We'll write yes. And maybe we'll go ahead and say 14.3 grams conserved. Okay, let's scroll down to, what's happening is it exo or endothermic when water vapor condenses? Well, as a general rule, if you're going from a solid to a liquid to a gas, it requires energy to go uphill, right? If you're going to melt something or boiling, it requires energy. That is considered to be endothermic. So the opposite must be true. As things condense or as they freeze, the process releases energy. It's exothermic. And water vapor condensing, that's going from a gas to a liquid. So that's that one. That must be exothermic. And let's do one more. Let's convert 210 Fahrenheit to Celsius. The formula is degrees Celsius is equal to degrees Fahrenheit minus 32 all over 1.8. So let's just plug in. Degrees Celsius equals 210 degrees Fahrenheit minus 32 all over 1.8. When we plug that in, we get 98.9 degrees Celsius, and that makes sense because we're just under 216, which I know is the boiling point of water, but we're not done because notice that we're doing both adding and subtracting as well as multiplying, so we need to take the most stringent result, right? This is a combo situation. So what do we have? 2. We only have one number in here. This is an exact number. In either case, we have 2 sig figs or the whole number. And so I think that we need 2 sig figs or the whole number in either case, right? No decimal places. And that would mean 99 degrees Celsius. And so I'm going to write equals 99 degrees Celsius and circle it, and we're done. One last one. I think it's one last one. We need to find the specific heat of a metal with a mass of 14 grams, heat of 2.45 kilojoules, and change in temperature of 3.2 degrees Celsius. Well, specific heat has the units joules per gram degrees Celsius, right? That means we can just take joules and we'll do it that way, right? We could just do it that way. You can also know that Q equals MC delta T. This is a longer way to get the same result. I don't think I'd do it this way. But if that is true, I guess that C, which is the specific heat, C must equal, let's see, I need M and delta T on the bottom. So I'm going to get rid of M by dividing it by itself. I'll get rid of delta T by dividing it by itself. And M over M is gone. Delta T over delta T is gone. C equals Q over M. In another event, now let's just, that's the same thing, right? This is joules per gram degrees Celsius. And so let's go ahead and do it. So it's joules is 2.45, but that's kilojoules. There's 1,000 kilojoules in a joule. So that is 2,450 joules. Convince yourself that's true. Gram was 14 grams. Wasn't it? Yes, 14.0 grams. Change in temperature was 3.2 degrees Celsius. C equals Q. Ah, there it is. I didn't divide both sides by delta T. Did you see that? There it is, delta T. Both sides you got to do it for. C equals Q over M delta T. Joules per gram degrees Celsius. And when you punch that in, I did that in advance somewhere, 2450, we get 54.7 joules per gram degrees Celsius. However, we're dividing, right? So the rule is we keep the fewest number of significant figures. 3, 3, and 2. I need this to 2 significant figures, right? I believe, yes, 2 significant figures. So I'm going to write 55 degrees joules per gram degrees Celsius. This is unfortunate because no substance ever discovered has a specific heat higher than about 4.2 joules per gram degrees Celsius. But at least we did the math right, and that is the answer to number 8. I hope solving those helped you a little bit, and that was some solved problems.